afternoon. How you guys doing? Doing all right? Okay, so today we're going to talk a bit about reactor analysis from the standpoint of, okay, how efficient is it? How do we describe that? How do we get some sort of efficiency term for how well it's performing, or how much something we're removing as a function of hydraulic residence time, as a function of the rate constants. So some piecing together the different things we've looked at so far, and doing a little bit of practice, just working through a few examples of that type of looking at an equation or looking at a system. So last time we left off with this example, and we went far enough to see that, okay, this is probably not first or second order. It's definitely not zero order reaction occurring. And so we could work towards plotting the data in essentially this form, and going from there. So the book had already kind of done that. I'm not planning to touch on it too much further, just as a reminder, though, that this is, if we set it up properly, we can get it in a y equals mx plus b type of form, and then solve for the n, which would be our rate order. So that was from last time. That's kind of just where we left off. There was one more thing I wanted to point out, and that is, what are some examples of cases where we have a non-integer order rate constant, or perhaps a system where we go from a zero order to a first order, or something like that. And it turns out that enzyme kinetics is a good example there. And the book takes an elaborate detour talking about it. So if this is particularly interesting to you, or perhaps if you're working with wastewater or cultures, things like that, may be well worth taking a look specifically at this portion. Essentially, the kinetics for a system where you have changing substrates or changing amounts of reactant, it can be pretty difficult to do the math if we don't reach a steady state. And so for the example of enzyme kinetics, when we have some intermediate species, that would be the ES here. If we have some intermediate that is very rapidly created and destroyed, or very rapidly destroyed once it's created, sometimes it can be pretty difficult, you would think, to handle that and say, okay, well, if our reaction depends on how much is there, but it's like disappearing so quickly, how do we get a handle on that? And so the plot here is kind of giving an example of that, where we have substrate here being removed, so maybe microbe food being removed over time, some product being made, and it's utilizing some enzyme to do it. And so maybe some sort of biological reaction where the enzyme is being produced. And so therefore we have some weird intermediate species here as well, which is not at a steady state. So the deal is, for systems like this, this is the Michaelis-Menten model. I think this was developed about 100 years ago, maybe more, for wastewater type of dynamics. Under certain circumstances, you will find that you can have an approximately first order reaction happening. So the conditions are such that you will follow first order, or let's say zero order at certain times, for some time. So in this example, we see low substrate concentrations. That's actually further along in time. So once we've reached a point where there's not much substrate left, not much food left for the bacteria to eat, we end up getting to a first order condition. And our product that we're forming is kind of asymptoting. Our decay of our substrate itself, that also looks like it's becoming exponential in terms of the decay profile. But during high substrate, maybe the first few minutes here, this is perhaps better fitted with a linear portion, right? So there are times or situations where, given perhaps this kinetic model of how much enzyme or how much intermediate do we have early on compared to later on, sometimes we can mix and match to get a model that will tell us, okay, when the Km here is much larger than the substrate, it will depend on a particular thing. Or in other scenarios, maybe we put a dependency on the initial amount of the enzyme that we have. So there are mathematical ways to set it up to say, okay, over here, we can see this dominates, and therefore it's going to be like a first order, and over here, it's maybe more like a zero order because one term simply is not important anymore. So I'm not asking you to learn or memorize this in particular. I'm just highlighting this as an example of scenarios where we might have, let's say, 0th order over there, and then perhaps first order. This would be decay with respect to substrate. Okay, so I thought that might be interesting. This is probably also where the Monod kinetics are coming from, if that name rings a bell, with the half velocity constant and all that. Okay. So I just wanted to kind of make that little aside. So there are some scenarios where we might end up seeing a mixture of kinetics for a given system. Okay, so mostly today I want to talk about dealing with reactors and their efficiencies directly. So with flow systems, many times we'll be looking at our CSTRs. We can look at the outcomes in a few ways, right? We could have, and we can do this in a steady state circumstance. That'll be usually how we set up a CSTR. If we want it to be running steady state and do our analysis accordingly. Of course, we can change that if we need, in which case our outcome is going to have some time dependency, right? So if I have a CSTR with something flowing in it, but over time what I'm feeding it is changing, that could mean we're not at steady state. Or we just initially started up a reactor. Let's imagine a scenario where we are starting a wastewater system, but we don't have a stable bacterial colony yet to do the consumption. Initially, we don't expect to have much degradation of our waste. Okay, so our efficiency would not be great. But over time, as we go towards a steady state, hopefully, perhaps we expect our efficiency to improve. So for a function like that, if we're looking at our efficiency or some outcome on a non-steady state system, we expect that this type of outcome parameter would be changing with respect to time. Of course, like I always say, we don't want that. We'd rather have a standard operation, consistent operation, and that's that. So that will be the typical condition. So we could look at net reduction. What's the difference between what we start with versus what we end with, right? We are reducing it by X amount, C in minus C out. We could look at what portion is remaining. So what is going out compared to what's coming in. So if, let's say, we had 1 out of 100, that's going to be 0.01 as a fraction, right? That would be only 1% is remaining. We could look at that then as the fraction removed, so 1 minus that. 1 minus 1 over 100 would give us 99 over 100, or 0.99, obviously. So 99% removed. Okay, so that's going to be a useful conversion thing to look at. And we could solve our mass balance and separate it for that specifically if we wanted to. It's also possible that we solve it for C in or for C out, and then if we know the other one or calculate the other one, we can just put this into our equation, or we can just solve for it this way. But what my point is, we can solve for, let's say, removal efficiency, we'll call it nu, C in minus C out over C in, and maybe if we want it in a percentage, we can multiply it by 100%. This by itself is a fractional efficiency, and if we could put our entire mass balance in terms of that. And then that would give us a way to get efficiency as a function of something like hydraulic residence time. Okay, so today what we're going to take a look at is a few different approaches to look at, okay, how efficient is this system given a particular parameter, or given all the parameters that are relevant. Okay, that's kind of giving us a little practice and a little more direction about what tools from a mass balance do we need in order to make some sort of design decision. Okay, a couple things we can look at. Here's a couple first order decay examples in a CSTR. On the left here we have the fraction of something remaining in a system, where we have a removal reaction occurring as a function of detention time. So this would be our tau hydraulic detention time, right? Well, I mean, I guess this is, yeah, that's probably the best way to say it. So we can take a look and see, given different kinetic parameters, so given different rate constants, how many detention times, or how long of a detention time do we need in order to achieve some fractional removal. So if we wanted to remove 90% of something, we could draw a line across here and see, okay, given some rate constant, how long does it take before we get there? Okay, and you see on the right side axis, this is just fraction removed, and the left is fraction remaining. So looking at a plot in this manner might be pretty useful, because maybe we have a constrained reactor setup such that we're limited on, let's say, flow rate. We have to treat a certain amount of flow, and now we need to know, can we change our rate constant, or do we have to just change our volume to have a bigger volume to achieve a different residence time? Maybe our reaction is limited to a particular rate constant. We know that, that's just the way it is, and therefore we have to build a bigger reactor because we have to treat the flow, right? That's pretty typical. When we have a treatment plant expansion, usually that expansion is meaning, well, we have to accommodate more flow, and therefore, we can't accelerate these reactions. We can't change, the chemical reaction that we're and what do? Well, we have to make the reactor bigger. Okay, so that can be a neat way to look at it, and you can see example values of a 0.1, a 0.3, 1, and 3 per minute reaction time, reaction rate constants. Another thing we can look at would be, instead of plotting the K directly, plotting different Ks on here, we could incorporate a K times tau. So K times our detention time. If you remember, many of our rate equations end up looking like, when we solve them, something like C over C naught equals e to the negative kt, right? Or take the natural log of that. So if we put kt as a parameter and plotted our fraction remaining, now of course in this example we've got the natural log there, but if we just plot something like C over C naught, which is the y-axis here, against kt, it's kind of like saying C over C naught is equal to e to the minus x. And there's our plot, right? E to the minus x will look like that. So that could be useful. Given some k, we can plot it in that manner and see, okay, under these circumstances, any given k, we can put it in there, and we know now exactly how much detention time we need to achieve a particular design goal. Okay, so fairly neat, not too complicated things of what we can do there. So I wanted to, and I did leave these notes here intentionally, because we've already done this and pretty recently. I wanted to get our minds back into the idea of deriving some sort of mass balance equation, right? So the governing equation for a system, and here I'm keeping the notes here to remind us the process we took for example, a first order decay of a steady state system. And here we're saying let's solve this for C over C naught. So for a CSDR at steady state, we have some accumulation rate overall that's set to 0. So our accumulation within our volume is 0, and that's going to be equated to Q times C naught, or C in this case. Q leaving and C going out, C out. Going to be relevant with some volume, so this will be our inputs would be QC in minus the outputs, QC out, plus our reaction term, and we said a first order decay, so this is going to be negative V K C to the 1 power, and this will be the same as C out, because whatever's leaving this well-mixed system is also what is in there at this moment. Okay, so when we take this equation and we go to simplify it, we can solve it for C over C naught. I like to go ahead and divide everything by Q. That'll give us C in minus C out minus V over Q, which is tau, times Kc. That becomes, we can put the C terms to one side and then factor out the 1 plus tau K, or factor out the C and we get 1 plus tau K, equals C in, and so ultimately we derive this expression, C over C in is equal to 1 over tau K. So we've seen that before, which is why I'm kind of breezing through it. You've done it, giving you a little practice with it. So given that, putting our minds there, let's do the same thing except solve for this in terms of removal efficiency. We'll see if we can get an equation in terms of nu. This is just testing our own algebra, and I didn't bring my old notes here, so I have to pass the algebra test in front of you myself too. And so we'll see how this goes. I always recommend drawing your system first, even if it's the same thing we just did. You guys get something? How do you feel about it? Not sure. Where did you guys start? Did you start with what we just derived, or did you start from the starting point? Or from the this starting point? Yeah, I'm looking for something in terms of tau and k for sure. Yeah, yeah, we don't have numbers for this one. Anybody else?
I just started from the definition of the efficiency.
And so what did you put in there? Like
that's the same thing as 1 minus c divided by c naught.
So then you just take 1 minus this guy. So that's a smart way to do it, because then you're just saying this is 1 minus 1 over 1 plus tau k. I like that. So if you see what he's talking about, what he did is he just divided the top and the bottom here by c naught, or he divided this through, right? So this becomes 1 minus c over c naught. So that sounds like a pretty straightforward way to do it. You could also try starting from here. This looks like messy algebra, but one thing to notice is that might actually be a little simpler than starting from here if you weren't going from, like, if you didn't notice this part, right? So you could think to yourself, okay, well, we at least could isolate c naught minus c, but of course now we have minus tau kc to deal with as well, and start working from there and trying to simplify. So it's going to be algebra one way or the other. I like Sumto's approach. Anybody else do something different or? Mm-hmm. Say it again. Yeah.
I made c solid by the formula. So I have c equals to c naught into 1 minus efficiency. So now it's substitute for my
I'm sorry, I didn't hear everything you said.
From this efficiency equals c naught minus c.
Yeah, from that.
I made c solid by the formula.
You did what?
I made c solid by the formula.
Okay, you put that in terms of c?
Yes.
Okay.
So after solving this one on the right side,
so
c over c naught equals 1 over 1 plus.
You solved that for c, and then put this in terms of c?
Exactly. So I now input this.
Okay, so you put our mass balance in terms of c, and then put it into there. Okay, that makes sense. So if we were to do c equals c naught over 1 plus tau k, which we can derive from here, then you put the c into there. So then you can say u is equal to c naught minus c naught over 1 plus tau k. That was the approach you took, right? Okay, cool. So as with algebra, there's a few ways we can begin it, or a few starting points we could take. Assuming we do all the algebra correctly, should all work out. And this, we could see this would cancel, be 1 minus, also cancel with that, 1 minus 1 over 1 plus tau k. So, cool. Here I was thinking to myself, this is probably the most straightforward way to do it, but I don't feel like dealing with this just yet. So glad you guys found some better ways. You could separate out the c and then manipulate it, but okay. Point is, a few ways to get at it, but ultimately we can put this in terms, we can solve it for efficiency in this manner, right? And the way to get there, I like these approaches that you guys took. So long as the algebra is good, we should get to the same spot. and we could set this up for a different mass balance starting point, right? For a system that had 2 streams coming in to 1 reactor, we could figure it out, right? We could still make an equation like that, accounting for the differences in the reactor itself, or in the mass balance itself. Okay. Now, from here, one thing we could do, and I realize I have some writing on the slide that I didn't realize was going to pop up in my way. One thing we could do from here is solve for tau in terms of nu. So taking this expression and essentially solving it for tau. So see if you can get an expression tau equals like that. I'm going to do what's coming first to my mind and then check in with you to see if you guys did something different. So feel free to take another minute or two. All right, so I started this one from here, because I saw we could easily solve for tau, and I just wanted to check, can I get this in terms of nu in some way doing that? So I just added tau kc to both sides. So I get tau kc equals c naught minus c, which is pretty close to this equation. And so I decided if I divide both sides by c naught, I'll have nu on the right. So that becomes nu when I have tau kc over c naught. From there, all I have to do is say tau, multiply by c naught and divide by kc. So tau would then equal our efficiency divided by k times c naught over c. Okay, is that what you got? Or we're going to get? Do you see anything different? Do you take a different way approach? Nu over k. Oops. Time, you said minus? Minus, excuse me. Nu over k times what? 1 minus nu? Okay. And what did you do to get there? Like how did you arrive to that? It's probably the same thing if we expand it out, is my guess. But I'm just curious where you started your derivation to get there. From this guy? Say it again. Okay. Yeah. Cool. Okay. And so you see that depending on which way you approach it, and if we were to, write this out, let's go ahead and do that. So let's just leave nu on top. And in fact, I guess in some sense I like your solution better because mine has c and c naught. So it would be nice to have it just in terms of efficiency. So really what I ought to do is convert mine into only efficiency instead of having anything else in there, right? So I like your approach. But just to double check real quick, if we were to say this is 1 minus c naught minus c over c naught, well, 1 minus the efficiency, what does that give us? Yeah. Anyway, I'm confident that will factor out. And I do like your approach there, because for mine, we probably need to manipulate this until we get it into efficiency as well. So we'll do that. Okay. Any issues? All right. Yeah. There you go. Another way to factor it would be to get it like that. All right. So let's try that for a zero order decay reaction. See what that looks like. So we can get to this again where we have C naught involved where we shouldn't, but we can kind of maybe use a little double check that the overall system will look like, and we just have to end up converting this into a new system. Or perhaps we ought to do like you guys have been doing and start from here and maybe solve this in terms of C. So when I just run this through, we can get this, but that's not quite what we want. So let's go ahead and solve it for C, for zero order decay. We would say C equals C naught minus tau k. So if we put that into here, we would say we can call this nu and say that's going to be equal to C naught minus C naught minus tau k, but this is all going to be parentheses there, divided by C naught. See what we get when we solve that. So I think if we do that, we can get, let's see, 1 minus, well, you know what, I'm just going to, we'll do this, C naught minus C naught plus tau k all over C naught. That didn't really help. Got to the same spot. Okay, so there might not be a way to get rid of the initial starting condition. And in fact, if I actually stop and think about it for a moment, should there be a way to get away from it for a zero order scenario? For a zero order reaction, does it depend on how much is there? No. It's always a set rate. So does the efficiency, will that depend on how much is there to start with? And the answer to that would be yes, because for a first order reaction, it doesn't matter how much is there, you're removing a portion of it over time. So it doesn't matter how much you start with in that sense. For a zero order reaction, basically anything that's not first order, our efficiency should be tied to how much we started with, right? So in this case, maybe I'm happy enough with that, because we got there this way too. Okay with that? Okay, so let's take a look at an example. Here we have a disinfection example, so we might be kind of starting to touch on a future topic, but we'll get there. But this will be largely focused on just the reaction and the kinetics and everything. So disinfection of the microorganisms is sometimes considered to be a first order reaction with a chemical disinfectant, something like chlorine. And for a given drinking water supply and a certain test organism, the first order rate constant is found to be 1.38 per minute. If 99% inactivation is desired, what detention time must be provided if the disinfection to be accomplished is it's going to happen in a CSTR? So just putting this all into one place here for you. I don't care which way you approach it. You could scroll back in our notes and start from one of these spots, or just set up your mass balance, right? And in fact, probably starting with a mass balance is a good way to go, but in general. right, so I'm curious, how many of you went back to the tau equation where we solved tau in terms of efficiency? Anybody? Okay, about half of you. How many of you went here and then just solved for C over C naught and plugged that in? A few of you? Okay. Anybody take a different route? Okay. Yeah, because we just spent all that time deriving things, and we could just say, all right, what was it? We said tau equals tau in terms of efficiency, take that and plug it in, right? And the efficiency was needed to be 99% efficient, right? Because it was removing 99%. So we could take that. That would certainly do it. We said that is, oops. One minus nu. Could do that, or the first thing that comes to my mind, just because I don't really look at it in those terms as often, would be to simply solve this for C over C naught, which becomes 1 over 1 plus tau k, but that's not super convenient because then we have to resolve for k, or excuse me, resolve for tau. But we can do it, right? So that's 0.01 equals all that. But this one's probably a little easier on the calculator, so we would say that's 0.99 over 1 minus that, 0.01, minus 1 over 1.38 per minute. Okay. And what's weird is this value, why is that not in minutes? There's no minus sign here. Okay, so I have that incorrect. That's a multiplying? Okay, thank you. So this is why you check your units. You find past mistakes. Okay. Okay, so what's that come out to? 71.74? Great. Okay. Fair enough. So the good thing is, in case you didn't happen to remember this equation that we derived, you could derive it for yourself from our mass balance and get there, right? The point really is that we can make nice, convenient parameters based on some efficiency, right? If we know the efficiency or the efficiency that we are targeting, we can just directly say, okay, it needs to have a retention time of this. Okay. And the book agrees, 71.7. Okay, let's take a look at another. Okay, with the same conditions as we just looked at, but now consider that the disinfection is to be accomplished with a plug flow reactor instead of a CSDR. Recall that disinfection is considered as a first order reaction with rate constant. For this particular scenario, the K is 1.38 per minute, and we have a 99% inactivation that we desire. What detention time must be provided if the disinfection is to be a plug flow reactor? Now, we haven't really talked about plug flow reactors today yet, but you should remember what we've talked about in the past. So good little challenge for you to recall that if you need. What's that? You could, yeah. Okay, how many of you are recalling what to do with the plug flow reactor? Some, I think some are not, but some are maybe? Some yes, some maybe. So that's the simplest way to do it is to model it as a batch reactor that's on a conveyor belt through a pipe or something like it, right? So remember that the way we define a plug flow reactor is we take some really thin slice, it's really small width here, and we say that little reactor is well mixed and at steady state. And then you have flow going through it to the next one. That's one way to do it, and that's the steady state approach, because we could get the whole pipe in a steady state, and each little tiny reactor would be at steady state, well mixed within itself, and acting like a little CSTR. But we need an infinite number of those, so we would end up, if we derive our mass balance for one of them as 1 over 1 plus tau k, we need to take that to the infinite power. In which case, if we were to do that and recall the Taylor expansion or whatever it is, we would end up finding the same equation as if we had a batch reactor that was just hanging out, doing its thing until it reached the end of the pipe. So the simplest way to do it would be to set this up as a batch, except instead of using time, we're using the residence time. And that's the real key, right? That's what connects, changes it from it's just sitting there to this is in a reactor that has continuous flow, okay? So we still definitely need tau as V over Q, but where we put it is essentially dictated by the T that we would normally use for a batch system. So for a batch system, we do not assume steady state if we have a reaction happening, because the only thing that can happen is our dc dt from the reaction. So in this case, a negative k c here to the 1 power because it's first order, and we do the integration and we end up finding the natural log of c over c naught because we do the integral of c over c. This is also in the volume. We do the integral dc over c. We end up with natural log of c over c naught is equal to negative kt. So with that, we say we're going to do this for tau time. And then our batch reactor model is sufficient Now we've contextualized it properly. Now we've incorporated the flow and the volume by doing that. Okay, so that would be the approach. You know, perhaps you could work with this. I don't recommend it. I don't have that knowledge on the top of my head. I think we probably learned it at some point in calculus, the Taylor expansions and how that would work, but just trust me that this works. But it also shows you that you can take a steady state approach through the reactor, and within the entire reactor, you can have a steady state in terms of you're not accumulating any, or one way or the other, any of our concentration as water is passing through it. So that all works out, and we can simply say the natural log of 0.01 is equal to negative K times tau and solve for tau. Anybody get that already? 3.38. Okay, so which would you use for a reactor? CSTR or a plug flow reactor? So CSTR was 71 minutes. Plug flow reactor was 3 minutes. I think maybe plug flow is better for this scenario, right? And what you see here is what's happening in the CSTR is as soon as you add in your concentration to this big tank that has already been reducing stuff, or like removing concentration, you have an immediate drop off. So your reaction rate that is first order depends on how much is there. But immediately as soon as you add it, how much is there has changed. Whereas in a batch reactor, you have a lot of time where early on, your net reaction is a large number because there's a lot there. So in the first few minutes, you have a fast rate of change because there's a lot there. Whereas in the CSTR, as soon as it enters the reactor, there's not so much there. And it's only ever changing the amount that's there at that particular rate. So that's a big difference. Plug flow reactors tend to do a lot better for treatment where you want to remove to a high percentage of removal. CSTR is actually pretty handy if you just need to get like a 70% removal, and it's pretty quick and efficient for that. Okay. Yeah, so 3.34 minutes. All right, we have probably time to look at one more, then we'll wrap up. So the very next example in the book says find the effluent concentration from a plug flow and a CSTR, each treating the same pollutant, each with detention times of 1 hour, with the following second order decay reactions. So K for the second order reaction rate is 0.2 milligrams per liter per minute. And the concentration in the influent is 100 milligrams per liter. So see how far you can get with that. This is calling back to the second order stuff, so that's, you know, might have to go back to our last set of slides to remember the derivations there. But give that a shot, and I'll work with it. Work with you on it. Let's assume steady state. We're still in class. All right, we'll do the full solution next time here, but at a quick look, I think if I recalled the calculus correctly, do you guys agree that the integral of dc over c squared is 1 over c minus 1 over c naught, or is that, do I have that backwards? I think it's 1 minus c minus 1 minus c naught. We'll double check that, but if so, then the rest of that derivation would follow. C equals 1 over negative k tau plus 1 over c naught. And then we have those parameters and we could solve it. Now the CSTR case, what's interesting is we end up with a quadratic equation. And so I think I've got, yeah, the quadratic up there just behind all this. I'm just going to erase this, move it out of our way. Have the quadratic equation here to remind us how we might solve that. And we could get that in this form from here and solve c equals -1 plus the square root of 1 plus 4 k tau c naught divided by 2k tau. So reminding ourselves of a lot of algebra that we haven't seen in a while. Okay, so that would be the answer for the CSTR once we solve that. And I think, actually, you know what, let me, we can check. I think the first slide, did I have, no, I didn't keep it, I should have kept it. We can look back at our last slide, so we'll do that next time. We'll lift up, we'll take off there, resume there next time. So see you guys on Thursday. And I think that last slide was actually it.